What I'm going to talk to you about today is functional safety and reliability and how it might fit into your general PLM process. Slightly different flavour to the two previous presentations you've just seen. I'm going to be looking at some case studies of how our functional safety and reliability work takes place, the kind of customers we work with, and what sort of solutions that we have. I'm also going to touch a little bit on the competitive edge and why the solutions that we provide can help you add value to your customers. So back at the end of 2021, PDS Vision purchased Wild Analysis, which is where I'm from, based in the UK. And our activities fit into the purple line you see there. And that's how we add value to the overall PLM process. We have two groups within the business. One's a CA simulation group, and we have a functional safety and reliability engineering group. And most of what I'm going to be talking about today is the functional safety and reliability activities. Now, what you'll see is that most of our simulation and functional safety work is best done as soon as possible in the PLM process. As soon as you can get that sort of analysis work done, you can save yourself a lot of pain, a lot of cost further on. With reliability engineering, that also takes place at the beginning of a program. But equally, if you've got equipment operating in the field, reliability comes into play to feedback how well your maintenance strategies are working to enhance the life of that product in the field. A little bit about Wild very, very quickly. We've been going since 1980, and these are the kind of simulation activities that we get involved in, from traditional structural analysis type work, fluid dynamics and EMC kind of activities, all done using the ANSYS toolset is the product of choice that we use, and we do our consultancy services and training courses as a support activity to encouraging software sales. On the far right, you've got some thermal management. So if people are involved in electronics or any heat transfer kind of activity, very, very powerful tool sets within ANSYS to be able to do thermal analysis. You can use, there's a product which I'll come on and talk about a bit later, where as an ANSYS product that focuses on using thermal management to help in the reliability of electronics. A little bit more off the wall, kind of more focused simulation activities we get involved in. If you're making plastic parts or if you're metal forming, we have solutions for analysing those sort of materials, not only in the actual manufacturing process itself, but also the manufacturing effects on the product. How can you maybe relieve stress in a product that you're making? And then finally, we have some skill set on being able to simulate the additive 3D printing process. A little bit more now about safety and reliability work. We kind of create an overarching umbrella of this called risk management. And for the purposes of today's presentation, I've looked at keeping safety limited to functional safety and human factors. There are quite a lot of other activities within functional safety that can be done. But for today, we'll talk about that. And there are two streams in reliability engineering. You have a design for reliability activity, which is where you're trying to encourage that the product you're making and selling is reliable or meets your reliability targets. Whereas the other stream in reliability is all about asset performance. How do I get the maximum, if I'm operating a generator set in the field somewhere, how do I ensure that I keep that going at a lower cost as possible? How many spares am I going to need? How am I going to do my maintenance strategies? How often should I be turning the equipment off to maintain it? But we'll come on to that in a bit later. So, a bit about functional safety. What I wanted to do first of all to say it's not this. It is not people taking risks to try and get tasks done. It is amazing the kind of lengths people will go to get a job done without taking that is unsafe, but it is not functional safety. This is not functional safety either, but this is more about the slips and trips that might happen. It might be that you've got a what kind of equipment do I need to keep me safe? That is not functional safety. that is technical safety, not functional safety. So there's an illustrative point here. This is a lift and how a lift might work. The lift doors are not functional safety. They're passive. They are passive, and they are known as technical safety. They stop accidents from happening. They stop people falling out or getting trapped as the lift goes up and down. But the functional safety element of it, which is what we're talking about today, is the sensors and the equipment that is used to prevent those doors from opening or closing correctly. And why do we need functional safety? Well, this is an American statistics chart that I dug up from the internet last week. It's interesting that in the US, the forestry and logging over the last 5 years, it's gone from 106 deaths or fatalities down to a minimum of 59, but is now on the increase again. So they're not there yet. There's still a long way to go to ensure that we keep these various industries as safe as possible. So we have to protect our workers, the public, and the environment. So the three elements within a functional safety system are the sensors, the logic solver, and the actuators. And I've given a couple of examples here, but they would typically include electronics, electromechanical software product. But here on the right-hand side, we have a valve, a controller valve that's in a pipeline, and it's a mixture of, you've got sensors looking at perhaps fluid flow, you'll have a valve mechanism itself, and there'll be some logic controller in there to ensure that if you're trying to maintain a constant flow of fluid through, that it's been constantly active. And then another example here is sort of a steering system from a variety of sensors. You might have 3 or 4 sensors. You might have tens of sensors as part of your control system. But equally, you've got your sensors, you have your electronic control unit, and then you have your motor to actually give you your power steering. So just a very brief overview of what that is. Very, very simple. That's initially. It gets a bit more complicated as you go a bit later on. So in the field of functional safety, most of this is driven by your industry that you're working in. So the father of all functional safety standards is the IEC 61508, which is the one in the middle. And from that, various industries have taken these standards from IEC 61508 and made them much more specific to the industry that people are in. So I'll give you a couple of examples a bit later on ISO 13849 for general machinery, and also the ISO 26262, which is for the automotive sector. Various standards are managed in different countries or different regions by these sort of groupings here. So from the UK, which is where I'm from, most of our work is in the HSE. And we talk about COMA, which is the control of major accidents and hazards. Whereas within the EU, you've got the European Commission and the Svescu directive. So depending on the industry you're in, the domains you're in, these are the standards that they refer to, the 26262, the ARP 4754 for the aerospace sector, and 61508 and so on, and 13849 for general machinery. There's lots of terms that are used and it gets very complicated. So we've provided a list of terms here. They all have the same meaning. They're just described slightly differently. So your safety integrity level for the car industry is known as ASIL. In the IS 61508, it's known as the SIL, so safety integrity level. Whereas in the aerospace, it's called the severity stroke probability, or DAL, as it's known as. So these are all the various tools and methods that are used within functional safety. They are all used slightly differently and in a slightly different fashion and using different kinds of data sets. But in essence, they follow a common approach, all driven by effectively 61508. So this is just really kind of illustrating in a typical project what kind of analysis you need to be doing in functional safety. And I'm not going to go through all the ins and outs of each one of these. We haven't got time for that. But it is a lot of consideration to take into account. It's a very complicated field, and you need to ensure that all these analysis methods that you're doing are done in a consistent, thorough manner. So it is very easy when you're starting off on a project to have lots of different spreadsheets, lots of different people doing different things. And it then becomes a bit of a nightmare managing that data. And I'll come on to how we can solve that a bit later. So a couple of case studies. A lot of words. Effectively, it's an audit of an existing power plant that is done for Smurfit Kappa, based in the southeast of the country. And it's basically ensuring that the functional safety work that was done 5 years ago, 10 years ago, is kept refreshed, it's kept live. It's basically an auditing process. So we wanted to make certain that if there'd been any changes over the last 5 years in the operation of the plant, that it wasn't creating problems from a functional safety point of view. So we did an audit on their data and made certain that all their documents from a functional safety perspective are up to date and managed. And that's very important when you have, as I mentioned, the health and safety executive. They'll do spot audits occasionally just to double check that your data is up to scratch. So this helps relieve that problem. So about 2 or 3 years ago, I was involved in securing some work from BAE Systems submarines up in Barrow and Furness in the UK. And they have a test facility which is used to test the equipment before it gets assembled into the vessels. And it is a very old set of equipment. And they'd had a few discharges of hot water into the local river. And so we were brought in to ensure that was, they've got the right processes in place to ensure it didn't happen again. So this is work we've done. It was about 3 months worth of work, all consultancy wise, but we used a structured what if analysis approach. So that's just one of the methods that you can use for assessing how your products can, or your system can fail, and what your remedial actions need to be to prevent it from happening again. So as I mentioned before, we're a reseller, like all PDSs, of ANSYS products. And we have sold several ANSYS Medini solutions in this last 12 months. ANSYS Medini is a tool that allows you to control better your functional safety data. And so it has made significant time and cost savings. It's reduced their time to market by about 40% in this instance. But it's bringing everything together into an integrated tool and ensures that everything is consistent. And that's the key thing we're talking about here. And the key role here is the model-based system engineering tool that is the kernel of what they do. And I'll show you a bit later how that connects to other systems. So very different company here, a company called Aldercote, who make lifting devices, so to get people to higher locations. And they were using or wanted to design their products to meet the ISO 13849 standard. And they were able to secure government grants to buy ANSYS Medini because it would make their business so much more effective. So in order for them to get a grant, they had to show that the grant would make them more effective and efficient. And the ANSYS Medini tool was the mechanism by which they could do that. So it's a really, really useful tool to bring your functional safety activities in focus, but in a consistent and cost-effective manner. And then the final functional safety example I've got here is a depot protection system, which is made by a company called Zone Green. And effectively, these trains need to be maintained. And so they need to be taken off the main tracks and put into a maintenance depot. And basically this system, the DPPS system, controls the positioning and the speed and the access of the train into the maintenance depot, because it'll locate where everybody is in the facility. So there's no chance of anybody being killed in that process. But the product they have is a competitive product, and there are other companies out there who have the same sort of product. Originally, this product was sold as a SIL 1, a safety integrity level 1 product, and they wanted to get to a SIL 2 level to make them much more acceptable for more projects. We work with them to help them achieve that. So we cover not only the hardware side of things, but also the software side of things. And now they're getting inundated with inquiries from people because they've now got a SIL 2 rated product. So that's been a very successful program. So the competitive edge bit, I've done this I've put forward a couple of questions that people might want to ask. So in terms of how can we maintain an auditable trail of functional safety documentation, talking about obsolescence management. There's a growing trend of old production fields, oil and gas sectors, fields in the European region particularly, where they may not have all the data they need. All the drawings might have been lost. There might have been paper drawings rather than CAD drawings. So they have an obsolescence management issue. How do we manage that? From a cybersecurity point of view, and perhaps an IoT thing that Carl Frederick was talking about earlier, is my plant at risk from cyber attacks? And finally, very common in certainly in the process safety side of things, there's a big skill shortage. So how can we address that? So here are some solutions. We've already talked about this one already for maintaining the auditable trail. So I won't go through that one again. But obsolescence management, we're working with companies where they scan data and they can, from that scan data, so if you can imagine a 10 square kilometre site, you've got thousands of bits of asset all over the site. How do I get that all digitized? So we use a scanning approach for doing that. And then we can take the data that's taken from there and working with a third-party company, we can turn that into intelligent data for what we call process and instrumentation diagrams, P&IDs. And once you've got that information, it becomes a digital thread, which you can then use further on down the line. So that's made a big difference for that. And it also reduces human error by collecting the data than you would do from traditional surveying equipment. So is my plant at risk from cyber attacks? Well, possibly. Can't say yes or no, but quite likely. So one of the ways that, from a wild perspective, we'll be working with Carl Frederick more closely on this in due course, is that we have experts who do cybersecurity work from a software perspective. And to get people started, we host courses. Typically, this one's an introduction to cybersecurity. So if you have equipment that might be susceptible to cybersecurity, we have a means of teaching your development teams how to avoid those sort of problems. It's interesting. Bear with me. It stopped at the end of the presentation. Here we are. Here we are. Sorry. So from the final question about we have a skill shortage, we provide a whole load of training here for a whole series of training courses for alarms management, process safety management, hazard and operability studies. This is a very common term in functional safety, certainly in the process industries, is HAZOP. So that's the sort of, I call that maintaining a competitive edge. It's typically people who've already got a plant. How do we encourage that plant to be safe moving forward? For where we're developing a competitive edge, where we're more in the product development side of things, then we may want to be looking at SIL performance again, but then we may want to start thinking about how we can, as things get more complex, we have more sensors, we have more electronics, we have more control systems, complexity will lead to inconsistency and inefficiency. I'll come on to how we can solve that. Also, linked to complexity, far too many point solutions, but it's difficult for people to walk away from Excel. It's the favorite for everybody. But also, how do we get product to market quicker than the competition? And that's where, for the first question up here, we'll talk about the example I talked to you about with Zone Green for the work we provide by enhancing their SIL performance to get better market positioning. But then what I want to come and talk to you about is ANSYS Medini. As you know, we're already an ANSYS channel partner. And ANSYS Medini approaches and addresses all these sort of issues that we're talking about here. So in a typical functional safety, in the automotive sector, if we're looking at 26262, these are all the activities in engineering that you need to be doing to be involved in. And not necessarily so much the PHA side of things, but certainly hazard analysis and risk assessment. And these are all the kind of activities that you should be doing that ANSYS Medini allows you to do. It has a link to, this is now Windchill, but where PTC Integrity is, it's now known as Windchill. But it brings together all your safety requirements and your various analysis techniques, and using the SysML approach with your system models allows you to build your Medini models effectively. And all these point solutions that you would have traditionally, you can feed into a common model. And there are various modes of data import in and out, whether it be Excel or whether it be through MSR XML, for example, for test management Excel. So JAMA and DAWS and so on, and PTC Integrity for the safety requirements. So it brings everything together in a very simple one tool. It also covers not just the functional safety side of things, but it also looks after the cybersecurity element. So you can simulate and you can or model your cybersecurity performance. So it's a common approach, common structure, just different terms. So for example, whereas before we've got FMEDAs and reliability, you've got asset identification, where you might be looking at attack trees there. You're looking at FTA stands for fault tree analysis. So there's a lot of commonality, and so this is a growing product which will grow as time develops. ANSYS Medini will have a significant amount of development going into it at the moment. But what's the evidence? We're saying that most of our projects that we get engaged with customers are bringing costs of functional safety and the time to do the work down by 50%, which is a significant saving. All because you're integrating a whole series of point solutions into a common tool. And using the MBSE approach, you're ensuring that consistency I've talked about. Equally as important is traceability, making certain that people, once you've submitted your documentation, people can then have a clear view of tracing who's done what when. And finally, most as importantly, is efficiency, making certain that you are achieving these 50% reductions. So that's functional safety. Go on to reliability. Unfortunately, reliability isn't the most exciting of subjects. It's a very dry subject. There aren't very good pictures. So a few words, and I'll try and keep them as brief as possible. So reliability engineering is the subdiscipline of systems engineering that just really ensures that the equipment or the product that we're talking about is going to function without failure. And then the reliability aspect of it is that the ability of that system to work under stated conditions for a specific time period. So that's the reliability. It's related to time. It's also reliability closely related to availability. So when we wanted to put our light switch on when we come into the meeting room this morning, we want to make certain that's always going to work. So it'll have a very high availability. If you're making a tank, let's say, going out to go to some war somewhere, you want to make certain that your tanks are available. They are going to be, when you need to get into that tank and go, it's available. And that's really driven by its reliability performance. And finally, the reliability engineering focuses really on the costs of failure. You're looking at systems downtime, your cost of spares, how much does it cost to repair my equipment, where the repair personnel come from, and also, more importantly, cost of warranty claims. So those are the basic fundamental descriptions of what is reliability engineering and reliability. So, and within this, you have talked about reliability being defined as a probability of success at a time t. Maintainability is the ease with which a product can be maintained. And that's where things like augmented reality can come into play. Because if you are working in confined spaces, or you're working on an oil rig, for example, and you want to maintain a bit of kit that is showing it's got a bit of a problem, but while I'm in the area, what else can I be doing? Because I need to put in access ladders to get to this very difficult point. So while I'm up here, what else can I be doing? And you can use all sorts of tools to help you, but augmented reality could help you doing that. Availability, I've talked about already. It's making certain it's available when it's wanted. But there's another phrase commonly used, which is called dependability, and it's a measure of the combined reliability, maintainability, and availability. But most people talk about reliability and availability. That's most of the people we deal with are involved in that. A little bit of a statement here, really, just to explain the subtle differences between maybe reliability and quality. So whereas quality is particularly key at ensuring that a product is going to work at any one point in time, particularly during the manufacturing process. So when it's made, it's going to work. But reliability takes it a lot further to say, well, it's going to work today, great, but what's it going to be doing in 2 months' time, or 6 months' time, or 10 months' time? So whilst we can't do reliability engineering without a reliable product at the beginning, the art of reliability engineering is to ensure that you've designed it, that it meets its intended lifetime. So I thought I'd put a chart up to make it a bit more exciting. This could model a human being's life effectively, because people die at an early age. There's an awful lot of us who kind of live for quite a while, and then as we get older, I'm getting a bit closer now, so it's a bit worrying. Then your failure rate is going to start going up. But this, in engineering terms, you're going to be looking at typically here electronics, where you've got burning or wearing failures. So yeah, that's a classic reliability curve that you might get. But I thought this might be a bit more important or of interest, because you can spend a lot of time in cost in making certain it's reliable, but that your costs after sort of post-shipment, they'll start, the more reliable you make it, the costs will go down for your post-shipment and will go up for pre-shipment. So you have that kind of sweet spot in the middle, which is where your post-shipment and pre-shipment costs be minimized. And that's where your reliability activities should be focusing on to achieve that level of performance. So yeah, some reasons very briefly on why you should be doing an engineering program, for reliability engineering program. A lot of people don't quite know that their products are working as well as they could be. They don't have any failure reporting information. They're not capturing failure data in their manufacturing process or in the field when warranty claims come in. They're not having a closed loop process to ensure that is being captured. Very common is that are your products over-designed? You may be finding that you haven't done enough simulation work that we can offer. But effectively, you could have an over-performing product that is costing you money. So you may want to be bringing costs down for doing that. As I mentioned to you before, products are becoming much more complex. And it means that whereas a product today might be working okay, when you add extra features to it, it might affect its reliability because there's more components. The more components you have in a product, the less reliable it's going to be. That's just a fact of life. So if you are making more features into a system or a component, that's going to affect your reliability. So you need to make certain that you're doing all the reliability work up front before launching that product. Quite often, customers will come to you from a particular, let's say, for example, defense sector. You've got to meet these standards. You've got to be able to demonstrate you're capturing your FMEAs. You're doing some reliability block diagrams. You're doing some, you've got a fracas system. Those are things you might have to do. But the most important bit at the bottom is your competition's probably doing it and you're not. So key thing is, if you don't do reliability, other people will. This is a quick chart as to how design for reliability might be installed into a business or work in a business. Whereas these are your various stages where you've got your defining your objectives, you're identifying your key reliability risks and so on. You're looking at a reliable design that you've analysed up front. You then start doing some development and testing work. You're doing some assurance work. And then in the post-production phase, you're ensuring that your products are being as reliable as you predicted they were going to be 3 or 4 years after your product launch. And these are the various activities. I'm not going to go through all of them here, but these are a set of all the typical reliability functions that you'd be doing in a design for reliability activity. And it's very, very comprehensive. But the key thing here is the most important bit is getting this bit right. If you don't get that bit right, then everything else won't. Always get it right at the beginning. A similar chart, I won't dwell on this one, but this is for asset performance management. So a couple of case studies. So one of these is a product called ANSYS Sherlock. And ANSYS Sherlock is a product that is using simulation techniques to help define the life prediction of electronic components. It focuses on physics of failure, and it is built up on a series of databases of knowledge that have been built over the last 20, 30 years of failure rates for various bits of kit. But one of the key things, when you're talking about reducing manufacturing risk, it spends a lot of time and effort looking at the design for manufacturability. How well am I doing my soldering? How well am I putting my silicon layers together? What's the intended environment in which these parts are going to work? If I have to ship my electronics from A to B, is the shipment protected well enough so that it doesn't get any harsh vibration issues happening in the delivery of those products? It takes into account all these kind of activities. Excuse me. So what we're saying here is that ANSYS is saying that up to almost 75% of product development costs are spent on a test, fail, fix, repeat cycle. And what ANSYS Sherlock is doing is making that process a lot quicker and being able to be much more accurate in modeling the performance of electronics in PCBs. Minimizing test failures and design flaws and getting you to market quicker, having more confidence in the performance of that kit. So on a typical example is a valve on a boat somewhere. The strength of a complete supply chain is often influenced by the guys at the bottom, the very basic suppliers. If you get it wrong at the bottom, it'll cascade upwards. And we were working with Hale Hamilton here to ensure that they performed their FMEAs that they have to do within their contractual obligations for the defence contract, and to make certain that they were doing it correctly, to the right processes, storing the right sort of data, and we gave them training in how to do FMEAs. And that was a very successful little project. But it works from the sort of quite low down in the tier supply chain all the way up to the very top. So another example here is a rail project. You won't believe the spec that goes into the paint finish on trains. It is very highly driven from a spec. You're not allowed to have a speck of dirt or a fly on the, for every morning when it goes into service, it's got to be really clean. So at the end of each day, these trains need cleaning. And you need to make certain that your cleaning system is available. Otherwise, you might have about 20 or 30 trains queuing, waiting to go through one train wash system. So the reliability performance of the train wash system is key. So are we okay for time? Yes, okay. So with for Garendale, we analysed the train wash system. And there's a common phrase here, which is RAMS analysis, reliability, availability, maintainability, and safety RAMS requirements. They were given targets by their client, and we worked with them so their design matched and met those target requirements. So a little example there. Data centers. Very, very highly reliable systems. They have to be, because if you can imagine that your bank keeps all your records in the data center, what happens if it goes down? I might have a backup somewhere, but that my data storage system could be offline for weeks and weeks if I'm not careful. So what they do is they have various levels of performance. And you can see here, tier 5, which is getting more and more common these days, a tier 5 data center means that in a year, for maintenance, it can only be down for 5 minutes and 15 seconds in a year, which is no time at all for doing anything. You can only get your spanners out in a couple of minutes. So you have to remedy this by having a lot of extra redundancy built into your system. So rather than having one generator, you might have 4 generators. And you might therefore expecting that in a typical year, 2 of those generators might fall out, but I've still got 2. So that's how you achieve your availability calculations. But we've done a lot of work using Relisoft. It's a product that we sell as well as ANSYS for reliability. And it's worked very well. So we have a good reputation in the field of data centers. I'll pass that one. It's a defense contract, which we're a big user of Relisoft, which has really helped. But I'm just conscious of time, so I'll pass on. So very quickly, we can talk about large systems, whole vessels. We can also talk about very small systems. And this is a signaling cable that's used, made by a company called Tratos. And they were looking to get work from Network Rail, who manage the infrastructure within the UK. And they had to show that they met the Network Rail design for reliability requirements. And at the time, they didn't. They called upon Wild to develop a process for them to follow, and then for doing the calculations so that once we've been through that once, they can do it themselves thereafter. But when we did the FMEA for the cable, the most significant cable failure is rats. And that goes into your FMEAs because rats bite the outer coating for your cables. And that's one of the biggest failure modes. It's one of those things, as an engineer, you kind of don't really think about. You just think about the flexibility of the cable. If I pull it, will it snap and that sort of thing, or heat it up? You don't often think about rats. And then a larger company we work for, medical company, one of the key problems is when they install their equipment in hospitals, they are allocated so much time to do that. And if they go outside of that time, they will get penalties from the hospital because they can't do surgery. It's all to do with patient care at the end of the day. So they have to be absolutely spot on as to the availability of their medical equipment. So, and typically the kind of reliability work we do, we save them $500,000 in terms of spares and lost, avoiding penalties. So very, very quick now. Competitive edge, these are typical challenges we get. I won't go through them all now, but you can see this one here, too many point solutions. It's quite a common phrase, and we'll come on to that in a minute. But quite often, people think, well, I've got a problem with my design. What do I do? What do I do next? Well, I'll come on to what the first step for that should be. We offer a service called a gap analysis. And that means it's sitting down with a client, and that's what we did with Tratos for the cable manufacturer. And really was to clarify what their objectives were from a reliability point of view, understand the business structure. Is there a culture of reliability or is there not a culture of reliability? How do you change that? How do you clarify the product characteristics? Understand the knowledge ability or the skill level within the client. And you might be already doing a lot of reliability work, but how do you grow on that? So we did that for them, and we came up with a plan as to what they should be doing. And they're now using that. 2 years later, they're carrying on using that same process. So all the other ones I'm keeping as under Relisoft banner. And these are the sort of activities that we talk about in reliability engineering, some of which you may know, some of which you may not know. But Relisoft is a tool set that allows you to do all that. So basically, it's not just thinking about your product you're making, but also your manufacturing process. Is that reliable? And how can I optimize my maintenance planning? So yes, you have a series of analytical tools and a series of management tools. So you've got in the purple line on the image on the right there, you've got various tools that analyze data and create predictive models. And then on the left-hand side, you've got more of the management side of things, which is where you're not necessarily, you're using engineering judgment, effectively. You're either monitoring data or you're using engineering judgment rather than just maths. These are typical questions that you'll get asked. I'm not going to go through them now, but those are typically what you would get asked in a typical reliability project. And you might have said, well, okay, from a program point of view, how do we ensure consistency again? Very much like we talked about in the previous slides on functional safety. How do we be efficient, consistent, and cost effective? So these are all the typical questions, and ReliSoft allows you to do all these. And this is a typical, the tools that are used within ReliSoft, where they would occur in a typical phase of a project. From very important in reliability, your FMEAs should be linking to your failure data, your fracas report. So your FMEAs shouldn't be done in the product design, then put in a drawer and forgotten about. It needs to be live, and ReliSoft allows you to do that. It's a big chart. I'll move on from that. But anyway, I just wanted to summarise that it's effectively, ReliSoft is the tool of choice. It's a well-known brand within the globe, providing those analysis functions and techniques that are all part of a reliability engineering program. And that's me done. So thank you very much.